you're trying to, say, minimize the number of cuts through a particular graph, and encodes that cost function into a quantum circuit with parameters. Those parameters I'm denoting by phi here. So the quantum computer's job is to evaluate this cost function via a particular parameterized quantum circuit. And then the classical computer's job is to essentially optimize that set of parameters given the quantum computer's ability to evaluate it. So there's this constant feedback loop between the quantum computer and the classical computer, where hopefully you get convergence towards some kind of optimal solution. So this is an extremely common technique in near-term quantum algorithms. So therefore, there's excellent resources for it. There should be some very nice Jupyter notebooks and documentation on it on the IBM Quantum Learning page. So the way that you could bring creativity to this is to think of an interesting cost function to optimize. Here I suggested some combinatorial functions, like I suggested max cut, but really any cost function that can be implemented locally. So when the qubits are next to each other, you can enforce a constraint on them. Any such cost function can be implemented by QAOA. So if you can think of an interesting cost function that maybe hasn't been tried before, maybe you can do something novel in this space. Another very common thing that's done in near-term quantum algorithms is simulate the physics of small chemicals or small molecules. So this is something you can even do on very few qubits, is embed the Hamiltonian of some small molecule using these Hamiltonian to qubit mappings. So the Hamiltonian of a chemical is described in terms of the dynamics of electrons, right? Maybe like the positions of electrons in various orbitals. Electrons are fermions. So encoding the states of these second quantized operators into qubits is a little bit tricky, but there's this excellent lecture by Antonio Mezzacapo that shows you exactly how to achieve this. Then once you have mapped your molecule onto the quantum computer, you can start asking questions about how different dynamical quantities evolve. Like, for example, if you're interested in the dipole moment, you can plot how does the dipole evolve as a function of time. So you choose an interesting observable, you figure out how to encode it within this Hamiltonian to qubit mapping, and then you simulate the dynamics of your quantum of your molecule on the quantum computer. So again, the way to be creative here is to think of interesting molecules and to think of interesting observable quantities to look at. I think that's this could be a very interesting project.
And also for folks who just joined, Patrick is giving some ideas for projects that you could do. And the slides and all the links will be public after the, are they already public?
They are already public. Yeah, we'll have a link to them at the end of the talk if you want, but yeah, there should be a link on the Slack somewhere if you want to access them. Right. So yeah, so these were a couple more introductory projects that I had in mind. Let's start going into projects that are a little bit more off the beaten track. Projects where there are still decent resources for understanding them, but maybe I haven't really seen them done at a quantum hackathon before. So one that I'm particularly excited about is quantum signal processing. Quantum signal processing is this key ingredient to this grand unification of quantum algorithms. So this is something, this is the title of a review article written by Isaac Chuang's research group a couple of years ago. It tells this really amazing story about how all these different quantum algorithms that were using very different techniques can be unified into a single algorithmic framework that relies on quantum signal processing. So for example, so the thing that quantum signal processing does is it applies a sort of function that you encode into certain phase rotations in your quantum circuit to any matrix or Hamiltonian that you like. So for example, if you want to do Hamiltonian simulation, you might be interested in applying the matrix function e to the ITX. If you're trying to prepare a thermal state, then you might be interested in this real valued matrix exponential. If you're trying to project onto the ground state of a Hamiltonian, then maybe a threshold function could work. So a function that has high support on the ground space part of the spectrum, like on low energies, but then no support on the higher energies. It will sort of filter out the high energies for you. Or if you're trying to, you run the quantum linear systems algorithm, you're trying to solve large linear systems on a quantum computer, you will have to compute matrix inverses. This can be done by approximating the function 1 over x. So this is incredibly powerful because of how general it is. And all of it relies on figuring out how to encode these different functions into these angle sequences. And that's what quantum signal processing is. So I think this could be a really exciting project. Find a particular application of quantum computers, figure out how to synthesize these angles, run the corresponding quantum circuit, and show that you're implementing this function in the desired way. Fortunately, the Tron group has some code already available for helping you synthesize these angles, but figuring out how to use it and figuring out how to turn it into a quantum circuit is still a little bit tricky. So that would be the challenge. Okay, moving on. So a very related problem is amplitude estimation. Now, how many of you guys have heard of Grover's algorithm before? Okay, so a good number of you. So Grover's algorithm is this tool for delivering quadratic speedups in a wide variety of Monte Carlo algorithms, specifically for like searching particular things. Well, amplitude estimation is sort of Grover's algorithm's cousin that aims specifically that targets estimation problems. So say you have some kind of quantity that you're estimating by taking the average of very many shots. That's a very common situation in Monte Carlo. Well, any such situation can be sped up quadratically in the accuracy using this amplitude estimation procedure. So it's a very widely applicable. And the way that it works, and maybe you can sort of tell based on the animation there, is that we start with a confidence interval that is guaranteed to contain the quantity we want to estimate. And then we choose a very particular set of Grover rotations that happens to tell us a lot about this value by taking a couple of samples. And then as we learn more about the quantity, we can start iteratively shrinking this confidence interval until it is narrow enough and we're happy with the confidence of our estimate. So this algorithm is described in this research paper by Grinko, and they have some code available for figuring out what number of Grover sequences is optimal at each particular step. However, I think you can do better than they do. I think it might be possible to come up with very clever choices of Grover rotations that let you minimize the amount of resources required to perform this kind of estimation. Right, and now we're getting to the advanced projects. These are projects that are a little bit harder. They might involve you trying to come up with your own quantum circuits. How many of you are familiar with quantum teleportation? Okay, so a good number. So quantum teleportation is this idea where Alice and Bob can send a quantum state from Alice to Bob without having any ability to transmit qubits. And the way that they achieve this is by using an entangled quantum state as a resource. So Alice and Bob start by sharing an EPR pair, an entangled state. Alice performs a measurement that takes her copy of the state that she wants to transmit and measures it together with her half of this entangled state. And this will result in classical data that she can then send to Bob, who can then correct his quantum state and obtain the quantum state that Alice initially had. So that's the basic idea. The issue with quantum teleportation, the way that it's taught in the textbook, is that until Bob receives those corrections from Alice, there's nothing useful he can do with it. If he wants to, say, continue computing with that quantum state, he won't really be able to do that until he learns what Alice's corrections are. So this is a problem that port-based teleportation tries to solve. It involves a different kind of entangled resource state that, as you can see here, has a bunch of ports on Bob's side. And the information that Alice tells him is not how to correct the state on his side, but simply which port contains the quantum state that she wanted to teleport to him. So I think this is a really clever idea. It involves a clever construction of the underlying resource state. But unfortunately, there are some research papers that go into how to construct such a state and how to perform a measurement on Alice's side that tells you the desired information. So I think this would be really cool if you could make this work, like if you could teleport a single qubit on a small quantum computer. And then finally, perhaps the most crazy project is to prepare a holographic quantum state. So maybe some of you have heard of the ADS-CFT correspondence. Maybe you've heard of like these ideas in quantum gravity. Can I get a show of hands if anybody's seen this stuff before? Okay, some people. So this is really cool. So this is basically what all the string theorists are doing nowadays. It's an idea where so maybe you know the story in quantum physics that we've always had so much trouble creating a grand unified theory that is capable of containing both all of the standard model physics that we see at the Large Hadron Collider, but also describes the general relativity theory that Einstein proposed. It's sort of hard to bring these into one framework. Well, one idea that's sort of in this headspace is to consider a gravitational theory, this so-called anti-de Sitter space. And if you choose your coordinates correctly, you can sort of define this gravitational space-time to have a boundary at the edges. And then at the edges, you place a quantum conformal field theory. And the idea is that any gravitational quantity, maybe the shape of this curved space-time, can be extracted entirely by looking at different properties of this quantum systems at the edge. It's sort of the universe as a hologram kind of an idea. So I think this idea is really fun. And the quantum states involved that are on this boundary have a very particular structure to facilitate that. Can you make a quantum state that has that structure and show that the space-time involved has that corresponding structure? I think that would be really fun. Now, in order to do this, you're going to need to discretize your system. In the standard anti-de Sitter space conformal field theory correspondence, this conformal field theory is infinite, right? It's a field theory. But maybe we can reduce it to maybe a couple qubits that we think of on a circle. Then it turns out that there's a way of thinking of these things in terms of quantum error correction. So I've linked you to a couple of resources there that show more or less how to do this, how to construct certain families of maybe 6, 7, 8 qubit quantum states that have these holographic properties and how to demonstrate them. But how to prepare them and how to show that they're holographic, I leave up to you. Right, so finally, let's conclude with a couple more open-ended projects. Quantum computers are inextricably tied to randomness. So a very nice idea might be to use a quantum computer to generate random bits. Now, of course, on its own, that's very easy. So maybe in order to make things more interesting, maybe you want to make the randomness certifiable. You want to use that randomness in some cryptographic protocol. I want you to prove to me that the randomness that you've generated is actually random and not some some bits that you sampled like 5 years ago and now are just recycling all the time. Maybe it can encode some kind of certification scheme into the randomness, special correlations that I can verify that prevent you from just reusing prior randomness. So I think that would be very fun. Another thing that I've seen a couple attempts at this, but I'd be really excited to see a quantum video game that really captures the intuition of quantum mechanics. One thing that video games are really good at is explaining, not mathematically, not intellectually, but intuitively what certain physical theories feel like. If you can find a way of explaining intuitively the weirdness of quantum mechanics via some kind of game, I think that would be enormously exciting. I've linked you here to a lecture by a famous video game designer who talks about the applications of video games in education. Maybe you can find something interesting to do along one of those lines. And then finally, in order to make quantum computing practical, if we want to run algorithms like Shor's algorithm, we're going to need to figure out how to do very simple things like just adding numbers, multiplying numbers, And this gets a little bit tricky because quantum computers are reversible. Whenever you perform a quantum computation, it's always possible to run an inverse computation that gets you back to the original data you started with. So working with that constraint and encoding interesting arithmetic calculations while still having that constraint can be sort of challenging. There's a couple approaches in this direction, but I think it would be very interesting to see if you could make some of them more efficient. So that's a ton of projects. I highly encourage you to ask us for assistance if you get stuck with any of them. Maybe something that you guys could do, if any of these projects sound compelling to you, is to get started with some of the readings that we linked and maybe give some of the associated math problems a whirl yourself. But if you get stuck sometime during the hackathon, we'll both be there. Please text us on Slack and we'll be there to support in any way you like. Okay, back to you.
Yeah, thanks, Patrick. So now I want to talk about some introductory Qiskit material. For those of you who haven't worked with Qiskit before or who haven't heard of it, don't have very much familiarity, I just want to give a brief overview. So Qiskit stands for Quantum Information Science Kit. It's a software development kit for working with quantum computers, specifically IBM superconducting quantum computers. So what Qiskit does is it allows you to write quantum circuits and build quantum programs or algorithms that you can then send off to be run on quantum hardware and return the results or read what the results of the computation on the quantum hardware are. So it's just like any other software development kit, except that now you're running on quantum hardware. So today, for folks who don't have Qiskit installed yet, I want to give like a little bit of an overview on how to do that, and also provide support for folks who need help debugging or getting Qiskit installed on their machine. So first, raise your hands. How many people have Qiskit installed? Okay, so a little more than half. Okay, cool. So that would be good. So for folks that don't have Qiskit installed, you may want to first download Anaconda, which will help you keep your workspace clean. So if you don't want to download Anaconda, that's cool. You can also just pip install Qiskit directly from the terminal. And I think what would be useful for everyone, because I'm guessing a lot of folks have worked with Qiskit before, but haven't actually run circuits on IBM hardware. Actually, yeah, how many of you have run circuits on hardware before? Okay, so much fewer number. So here's what we'll do. For folks that haven't downloaded Qiskit, what I would like you to do is open up your terminal and try pip install Qiskit. If you have trouble with this, let me know, and then maybe we'll circle back and have you download Anaconda and get the workspace in order. For folks who have installed Qiskit, what I would like you to do so that you can run circuits on IBM hardware, if you haven't done this yet, is go to quantum.ibm.com and click continue with, or sorry, create an IBM ID. And you'll just put your information and your what school you're from. And this will give you access to an API key, which will enable you to run on quantum hardware. So I'll give everyone 30 seconds or a minute to go ahead and do this. And for the folks who are downloading Qiskit, let me know if you have any questions. Just raise your hand and I'll come and help if you need any help. So yeah, I'll just let you guys work on this for a minute. Yeah, I'm just having people create their IBM ID.
Okay, excellent.
Yeah, I'm trying to figure out when this ends.
How do what?
I'm trying to figure out when this ends. It might be like.
No, it's at 45. So we have quite,
Oh, we had an hour.
yeah, we have a full hour. We've got tons of time.
Okay.
Now we stormed through those slides. Might have been good to let people stop for questions.
Are people still working on getting the IBM ID? Yes. Who is still working? Few people. Okay. Give it another 30 seconds. So when you guys do get signed in, what you'll do is you'll see in the top right this little person icon. You'll click on that and go to manage account. And then under there, you'll see this API token. And you'll want to copy this.
So if I haven't signed in for over a year,
I think you should be okay if you haven't signed in over a year. You just have to. Do you like not remember your password?
yeah, I love.
Can you create a new ID?
Yeah.
Awesome. So I'll head over to the next slide. Please let me know if you want me to go back, or if you need any help, just raise your hand or Patrick can come around. So the next step will be to either create a Python file or pull up a Jupyter notebook. And the API key that you just retrieved from the website will go in this command here. And I will walk through each one of these things. And it would be good if we could have everyone like write, probably write this code. We don't want to run on the back end because then we're going to overload our back end of everyone and here is running it, but we can either switch to a simulator or just have this code, see that it runs and then cancel your job. So I'll just go ahead and start explaining the code briefly. Does anyone want me to hold on before going forward, or is everyone ready? Okay, yeah, looks up. One more minute. Okay, cool. That's all good. Yeah. Okay. Yes.
As we get some access to some sort of discussion, are we restricted to the 10 minutes?
Yeah, but it's like 10 minutes runtime,
Okay.
which is a lot of time.
Yeah,
Yeah.
okay. But in case we should run out, we'll reach out to you.
Yeah.
Okay, good.
Let's see, I think. I also just realized that you guys will need to pip install Qiskit IBM provider. So, yeah.
This one's really good, by the way. Shouldn't check it out.
Okay, so I'll go ahead and start explaining each line here. So at the very top, we have a package called Qiskit IBM Provider, which is separate from Qiskit, which is what enables you to use the backends, which we call providers. So you'll actually need to pip install Qiskit dash IBM dash provider. I know there are underscores here. I think if you use underscores in the pip, it'll also work. But yeah, so you'll have to go download that package. And then you'll just import IBM provider, which is how you access your account. So the next line, IBM provider dot save account. This is what will allow you to run the quantum circuit through your account. And this API key, which I have here, you'll replace this with the API key that you copied from the website on the last slide. And I believe you put override equals true. I think that means every time you run it, it like updates. Then you'll create a quantum circuit. This is just some random circuit that I created for a project I was working on. So it could be any circuit, so long as it runs and it's not more qubits than the device that you're going to run on. This is where all of the work from the hackathon is going to come in. Right now, you can just have this like empty circuit that's initialized to zeros. But most of what you'll be doing during the hackathon is trying to come up with circuits to run on quantum hardware. So the next step is once you have your circuit, how do you run it on the hardware? So the first thing that you do is define the backend, and you're going to use a provider, which I realize I defined somewhere else. But I can help you guys with that. So, actually, no. From Qiskit, actually, you import provider. So you'll just do provider.getBackend, and then you'll use whatever backend is available to you. So in the IBM Quantum Platform website, there will be a list of backends that are available to you as free users. And the code, like it'll be IBM underscore and then the name of the backend, which will be some city somewhere in the world. You'll be able to retrieve that backend. And then the way that you run your circuit on that backend is by using this .run command. So backend.run, and then this is the name of your circuit, and this is the number of times that you want to run the circuit on the backend. Okay, so once you run the job, which you'll be able to see it running in the IBM Quantum Platform GUI, there will be a tab that says jobs. You can go there, and then you'll be able to see the job running, and then it will be complete, and then you'll also be able to get a job ID. So if you want to repeatedly access the results of the job, you can use that job ID. But another way to do it is by just doing job.result.getCounts. And this will work the first time you run the job. If you run more jobs, then you'll have to use the job ID to go back, because you'll be overriding the variable job. And the get counts is how you get the actual results, because you'll be doing measurements. And then your measurement results will be, some qubit like 0, 0, 0, 1, 0, etc. And then plot histogram. This is how you would visualize the results, and it's our standard way of doing it at IBM. Okay, now I think is a good time. Are there any questions about the setup from top to bottom or getting the code to work? Yeah. What's that? Yeah. So at the top, you'll have to import Qiskit.
Okay.
Or it should be, yeah, from Qiskit import star, which is how you import everything in the package. Yeah.
So quantum circuit is fine.
Quantum circuit is not, yeah, okay, exactly. So at the top, I realize I should have added in this extra import here. So yeah, from Qiskit import asterisk, and this will import everything. So you'll get quantum circuit and you'll get provider. Provider, okay. Let me check my file. I might have defined the provider elsewhere. Yeah, okay, that's my bad.
Wait, it's not okay.
Okay, yeah, so provider, you'll also insert that provider equals IBM provider line. So yeah, this is how you get provider.
I think circuits are undefined. So these would define them somewhere.
Yeah, sorry. So you have to run these 2 lines.
Okay.
Yeah. Things working for you guys? Yeah. Oh, I think plot histogram is from HisKit. Yeah. Is it not working for you?
I think I need to report it. Not
Okay.
Or hash.
Oh, this is an asterisk. Is there an is it running? Because sometimes I import and then it still shows yellow, but then it runs. Like there. That runs. Yeah. Did you put in your API key? Okay, let me see.
Well, there's what ideas.
Oh yeah, so the provider.
So that's really basic.
That very good. You will have to look at
I know I headphone.
Okay. Hey everyone. So I think some of you are running jobs and they're taking forever to run. So the way that you check your jobs is by going to the Quantum platform and clicking under jobs, and then you'll see the list of jobs that you've submitted, and you'll also be able to see where you are on the wait line. And under compute resources, this is where you can see all of the all of the quantum computers that you can run on. And let's say like we click on Sherbert, for example, you'll be able to see how many jobs there are pending. And this is how you know what device you should be running on. So you try to find the device that meets your criteria. So it's the number of qubits that matches your circuit, or more than the number of qubits that is in your circuit, and also the like least number of pending jobs. Because this, it could like if there's 100 jobs in front of you, it might take a while to run. Yeah, so choosing which backend, you go like so in the IBM Quantum platform, and then you choose the name. So like if you're running like a 5-qubit circuit, you can choose a 5-qubit device. If you're running a much bigger circuit, then you should run a bigger device. And then you should look at the like the number of people in line. So like the number of jobs who are in front of you, because if there's like a ton of jobs in front of you, you might like your circuit might not run for a while. Sure, yeah. Let me show you. So for example, yeah, so like under compute resources, you can see like which one, right? So like here's Brisbane, right? So we can click on Brisbane, and then we see 534 jobs. Yeah. Or well, usually what I do is I split the like run part of the job into a different section of the file, or like in Jupyter Notebooks, a different cell. And then I just like run the job separate from everything else. Yeah. 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 Unfortunate at this time, but yes.
So we will have to have the waiting queue. Like waiting queue for the
Yeah. So but there's a good number of machines, so you'll just have to choose ones that fit your need, and also hopefully don't have that long of a queue time. Yeah, unfortunately. Yeah. Okay. How is everyone doing on this? Are there any more questions? So I added
Open that and. Yes, it's already. Already. Down there. People seem to.